Welcome to Lesson 2 of Block 2. In this lesson, we're going to get our first taste of orbital mechanics, also known as astrodynamics. But understanding orbits is quite a bit to bite off all at once, so we'll break this topic into two parts. This is part 1. Zooming once again into our course roadmap, we see where this lesson fits into the big picture of the entire course. The primary reference for this lesson comes from Understanding Space and Introduction to Astronautics, Chapter 4, Section 1. We recommend you read through this section either before or after watching this lesson video. In this lesson, and in this entire block, we'll focus our attention on the trajectories and orbits element of our space mission architecture. The discussion in this lesson will begin with a big picture look at what an orbit is. Then, armed only with an understanding of gravity, we'll examine the mechanics of orbits using some everyday examples, rocks and baseballs. Finally, we'll see just how fast you need to go to actually get into orbit. After you complete this lesson, you should have a good idea of what an orbit really is, and how to put an object into orbit and just how fast it needs to go. Before jumping into orbit details, let's take a little comic detour to see another explanation of how orbits really work.
Peter, I think maybe you're in denial about this fat thing.
Oh, yeah? Well, I challenge you to prove to me that I'm fat.
Okay, hang on. See this?
Yeah?
You know what it is?
Duh. It's an apple.
Good, good, good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Aw. Aw. Aw.
Humor aside, as we begin our discussion of orbital mechanics, it's useful to start with a big picture view of what an orbit really is. In the most basic sense, an orbit is like a big racetrack around the Earth, on which satellites travel around and around, sometimes up to 15 times a day. From their vantage point in these racetracks, satellites gaze down at the Earth below or stare out at the heavens, depending on the mission. But regardless of what they do while in this racetrack, the satellite will happily complete lap after lap, day after day, year after year, pretty much stuck on their racetrack. Keep this image in mind as we go through our orbital mechanics discussion. It turns out, and we'll see exactly why in later lessons, that the bigger the racetrack, the more energy it takes to put a satellite into it. To understand how satellites get into these orbital racetracks and stay there, we start by reviewing what we know about how gravity works. Recall that the famous Greek philosopher Aristotle reasoned that a heavy object should fall faster than a light one. Unfortunately, he never put his conjecture to the test. This had to wait for Galileo more than 1,500 years later, who proved Aristotle was wrong, when he observed that in fact all objects fall at the same rate once you account for their air resistance. Newton, with his law of universal gravitation, would later explain why this had to be the case. Most of us are okay with simply dropping two objects and seeing them fall at the same rate. But what if an object is in motion? Does that change anything? We want to understand this question in detail, because this is the heart of what we'll need in order to put something into orbit. To keep things simple, let's start with the challenge of putting a baseball into orbit and break the problem down to see what it really takes. Start by imagining two baseball players as shown in the figure in the upper right. One will drop a baseball and the other will throw a ball horizontally at exactly the same time from the same height as the first. Which ball will hit the ground first? They'll hit at the same time. Gravity doesn't care that the second ball happens to be moving horizontally at some speed. It's still going to fall just as fast as the ball that was simply dropped. Both are falling at 9.798 meters per second squared at sea level, regardless of any motion. If you still don't believe me, let's watch this video, which replicates our baseball example in the lab. It captures the result with high-speed cameras. Whether you drop a ball or throw a ball, they still hit the ground at the same time. Now that we understand how a moving baseball will behave under the influence of gravity, let's zoom out to look at the size and shape of the Earth. If we assume the Earth is perfectly spherical, which is close enough for our initial understanding of orbits, then for every 8 kilometers you go out horizontally, the Earth curves away 5 meters. Keep this in mind as we get ready to throw some more baseballs. We can now perform a little thought experiment. Imagine we build a small tower on our perfectly spherical Earth that's exactly 5 meters tall. On that tower, we're going to attach a very long cantilever diving board that is 8 kilometers long. Ignore the natural sag you would probably see. Imagine that this diving board remains perfectly horizontal, attached to the tower at one end. If you were to walk out to the edge of the diving board and look down, the surface of the Earth would be 10 meters below you, because you started 5 meters high and the Earth has curved away 5 meters. With our experiment all set up, let's see what happens if we could throw a baseball really fast from a height of 5 meters at the top of our tower. Imagine we could throw the ball 8 kilometers per second horizontally. We'll assume zero drag due to air resistance, just to keep things simple. How long would it take for the ball to reach the end of the diving board? Well, 1 second, of course. Now, how far would the ball fall due to gravity in 1 second? Doing a little math, knowing that the Earth's surface gravitational acceleration is 9.798 meters per second squared, it works out that in 1 second an object falls about 5 meters. Remember how much the Earth's surface curved away 8 kilometers downrange? 5 meters. So the ball started 5 meters above the surface. We threw it horizontally at 8 kilometers per second. 1 second later, it reached the edge of the diving board. But in that second, it has fallen 5 meters, while the Earth has curved away 5 meters. So the ball is still 5 meters above the surface of the Earth. What happens 1 second later? The ball goes another 8 kilometers horizontally and falls another 5 meters, and the Earth curves away yet another 5 meters, and the ball is still 5 meters above the surface. We have put the baseball in a circular orbit around the Earth. It turns out that as I throw balls at slightly different speed, you'll see different shaped trajectories. At any given altitude, there's one and only one velocity that puts you in a perfectly circular orbit. If you throw a little slower than that, you'll become an intercontinental ballistic baseball on an elliptical trajectory that intersects the Earth. A little faster, and you enter an elliptical orbit around the Earth. If you throw the ball really, really fast, the ball will travel out to the edge of the Earth's gravitational sphere of influence and enter its own independent orbit around the Sun, the same as the Earth's orbit, but it won't really go anywhere. If you want the baseball to go somewhere, you need to throw it faster still, so it leaves the Earth on a hyperbolic trajectory so that it can take it someplace interesting, like Mars or Jupiter. But no matter how you throw it, the shape will either be a circle, ellipse, parabola, or hyperbola. We'll see exactly why that is in the next lesson. It's much easier to visualize orbital motion using simulations and animations. Throughout this course, we'll use animations developed using Satellite Toolkit, STK, provided by our academic partner, Analytical Graphics, AGI. This simulation shows our baseball example starting from a slightly higher platform so we can better see what's going on. As we start the simulation, we're going to launch 6 baseballs at 6 different velocities. 4 are too slow to enter orbit and impact the Earth at some distance downrange, depending on their initial velocity. However, 1 ball has just the right velocity to enter a perfectly circular orbit. The last baseball is launched a bit faster, so it enters an elliptical orbit. With this idea in mind, this clever animation from the Vancouver Film School shows the fun an alien could have on an airless moon with just a baseball or a rock. From our baseball tower example, we can reason out the velocity we need to achieve orbit at the surface of the Earth. But it turns out we can calculate this value exactly for an orbit at any altitude using the relationship shown here. Right at the surface, as we already showed, circular orbital velocity is nearly 8 kilometers per second, which works out to 17,600 miles per hour, if you'd rather think in those units. The important thing here is that the velocity you need to be in orbit only depends on the body you're orbiting, in this case the Earth, and your distance from its center. As an example of orbital velocity, let's watch the launch of the Space Shuttle in this Satellite Toolkit simulation. Watch the velocity as it climbs into orbit. At burnout, the shuttle is going over 17,000 miles per hour. That's about 7.9 kilometers per second, which is exactly what our equation would predict. In this lesson, we learned that we can think of orbits as giant racetracks upon which satellites complete their laps day after day. Conceptually, putting an object, whether it's a baseball or the space station, into orbit requires we give it enough horizontal velocity that it literally falls around the Earth, never quite hitting it. The Earth's surface curves away as fast as the object travels downrange. We learned we can easily calculate this orbital velocity, which turns out to be about 8 kilometers per second for a circular orbit near the surface of the Earth, and decreases with altitude. That's it for part 1 of understanding orbits. In the next lesson, we'll build upon the concepts we learned here to gain a better appreciation of how orbits really work.